Okay, welcome to the physics class for October the 13th. Before we get started into the physics, there's a couple administrative things we need to talk about. So first off, I've been looking at the schedule and trying to figure out whether or not we have enough time to squeeze in one more test before the term ends. Theoretically, we could do it. We would have to rush through the material a little bit faster than I think is a good idea. I think you guys would appreciate if we don't rush, if we just go through at the normal speed and make sure everybody's well prepared before we take the next test. I figured you guys would appreciate that. And I took a poll of the other class and they overwhelmingly said, yes, that's what we want to do. So I'm assuming that you guys are the same way. So then, yeah, we're gonna, rather than finishing up chapter 5 this time, we're just going to do part of chapter 5 this time, part of it the next time, and then we'll have time to review. So we'll be taking our next test right after the new term starts, not before. Now, for some of you, that's good news. For us, others of you is not such good news. Some of you didn't score very well on that first midterm, and you were probably hoping that you could use the next midterm as a way to pull your grade up. So if you are one of those, then there's two things that you should know, or that you want to know. One is that what I've decided to do is I'm going to take that test rework assignment, which was due last Saturday at midnight, which, by the way, one or two of you still haven't turned in, which is pretty amazing to me. It's worth 52 points, 5 times as much as regular homework assignment. And some of you blew it off, but most of you, almost all of you did do it. So I'm going to take that and I'm going to go into Aspire and I'm going to move that from the homework category into the test category. But I can't put it in there as 52 test points. That's just, it's not worth that much. That's not fair. So what I'm going to do is I'm going to rescale it so that it'll be worth 20 test points. So if you got all of them right, you'll get a 20 in there. Now that doesn't mean it replaces your previous test. It just goes in as if it was another test. But the test was only worth 20 points, as opposed to the original was one was worth 100. So if you did the test rework and you got them all right, it will pull your grades up a bit. And if you didn't do the test work, well, it's going to pull it down. For if you're one of those few people who didn't do it on time, tell you what, I'll let you turn in late. It'll cost you a late pass. Now you better have a late pass. If you don't, some of you have used up all your late passes, but if you have a late pass, I'll let you turn it in. But I can't give you full credit for it. That's not really fair. So the most I can give you is 15 out of the 20 points. Okay, now the other thing that's worth mentioning is extra credit. So you guys know that there is extra credit available, and you hopefully know that the way to get extra credit in my class is to go on to Canvas and look at those videos that I posted there. Let me share here. So there's a couple things that you need to know that you might not. Okay, so while we're waiting for Canvas to call it up here, when you watch these videos and you answer the questions that are listed in these videos here, you have to do it before we talk about that particular subject matter in class. And so next time we meet, I intend to talk about some of this material in class. So that means you've only got like 1 or 2 days left to do these 2 assignments. Now I've got a whole lot of assignments on there, so you don't despair. So if you look on your screen now, you should see the modules page from Canvas. So this assignment right here, these are videos that are created by former students, and this is what I like to call physics of everyday life. And then if you look down here, you see videos that I have created that are all sailing related, because as you know by now, the best way to learn physics is to go sailing, at least in my opinion. So when you click on here, it takes you to a whole bunch of sailing videos. So the first 2 are ones that I intend to talk about next time we meet. So if you don't do these first 2 ones by the next time we meet, you won't be able to get extra credit for them. Now, there's still a whole lot more. If you scroll down here, there's a whole lot of videos there. Okay, so there will still be lots of opportunities. This first video here is a continuation of what we started the other day. So this talks about planning a sailing trip from Miami to Bimini. And last time we met, we talked about the fact that if you point the boat straight east, but the Gulf Stream is carrying you north, so you end up kind of going northeast-ish. And we calculated what that angle was that we would actually go. But then we never finished the job. And so in order to get the extra credit here, I want you to finish the job. I want you to, so hopefully you recognize that what we need to do is we need to point the boat somewhat south of east. But the thing is that most students, they think, okay, well, last time when we calculated what the angle was north of east, that the Gulf Stream would carry us, however many degrees that was, students think that what we can do is then just point the boat south of east by that same amount, and that'll make it so that the boat ends up going straight east. Doesn't work that way. And I don't want to say anything more about it because I intend to talk about it next time. But if you can figure it out on your own, what direction to point the boat to make it so the boat goes straight east, even when you got the Gulf Stream carrying you north, if you can figure it out on your own and write up what the answer is and how you got the answer, then I'd be willing to give you some extra credit for that. But you got to do it before we meet next time, because I'm going to go over the answer next time. Same thing with this one over here. This is a video that Mrs. Whitbeck and I, Mrs. Whitbeck Zacharias and I jointly created together. We were sailing together with Coach Miller from the chemistry class down on Utah Lake. And so I don't want to talk about it other than just if you watch the video, you'll see what I hope you'll agree is an interesting physics problem and that we solved by using physics. So again, if you answer the question that I ask in the video here, I'll give you extra credit, but only if you do it before we talk about it in class, which I intend to talk about next time. All right, so do not delay if you are planning to do those for extra credit. And remember that the most you can possibly get from extra credit is 1/3 of a letter grade. You know, you can go from a B- to a B, but that's it. Or you can go from B+ to an A-, but that's it. You know, you can't go from a C to a B using extra credit. That just doesn't work. All right. So any questions about that before we move on? Okay. Okay, so the question from Calvin is that credit per video or all of the extra credits? Yeah, so all of the extra credit together that you might choose to do cannot possibly raise you up by more than 1/3 of a grade. So then the question always comes up, well, if I do one video, will that give me all of the credit? And the answer to that is, well, it depends on which video you do, and it depends on how thorough you are in writing up your answer. Some of the videos ask questions which are easier than others. So if you pick one of the easy questions, you're not going to get the full bump up in points that you would have got. And also, if you pick, let's say you pick a medium level difficulty question, if you just give a superficial answer that doesn't make it look like you did much study or much thought, I'm not going to give you very many points. But if you write up a really thorough, in-depth report where you include a couple example calculations and really do a good job, I might give you the full 1/3 of a letter grade just from that one video. So I can't really tell you in advance because it depends on the video and depends on your response. Yeah, what I'm talking about right now is extra credit. It's not a required assignment. It's extra credit only. If you don't want to do it, you don't have to do it. All right. Okay, one other really important thing is last Friday from 9 o'clock until 10:30, I was here on Zoom offering tutoring help. And some students joined and they asked some questions, and they were really very important, thoughtful questions. And by going over the answers, I think that they learned a lot. And you guys could have had you been here too. So you need to think about attending these Friday tutoring sessions. Unfortunately, I can't always guarantee that I'll do them because During the time that Mr. Wilson has allotted for us teachers to do online tutoring, which by the way is from 9 until 10:30, sometimes I have to teach the U of U physics class then, but other times I don't. It's kind of funny how the schedule works. So last Friday I did not need to, and this coming Friday I also don't need to. So I will be available on Zoom Friday from 9 until 10:30. If you would like to get some questions answered, I highly, highly recommend that you participate. Now, I did record the last session. I haven't put it up on Zoom yet. I think I will put it up on Zoom, but I don't guarantee that I will always put the tutoring sessions up on Zoom. I might not. Okay, with that being said, okay, let's get into the physics now. So let me share my screen here and show you the answers to last night's homework, at least the ones that you haven't already looked up. So here are the answers to the homework. If you'd like to see all of the questions, well, I got bad news for you. It's not going to work that way. I don't have enough time to go over all of them. So I could pick, say, 2 problems, and I'd be willing to do 2 problems, but I think that's all we really have time for. So Aurora just asked an interesting question. She said, if you don't have any particular questions, but you want to show up on Friday, is that allowed? Absolutely. Yeah, just sit there and listen to the questions that the other people ask, and there's a good chance that you're going to hear their question. You're going to say, oh, yeah, oh, it's a good question. I wish I'd thought of that. So absolutely, for sure, show up. Okay, any questions to last time's homework?
Could we go through question 8? I wasn't exactly sure how to do it.
Okay. Question number 8 is one that every year I have students ask me about that. And what we find is that most of the time it's not because they don't know the physics, it's because the question is worded in kind of a weird way. The author really should have worded it differently. If I were to have worded the question, I would have definitely worded it differently. So what we've got on problem number 8 is we've got a swing, child's swing. So here's the swing, and we got a rope coming off at an angle that's holding it up. Got another rope coming off at an angle that's holding it up. And what do they say the tension is in the ropes there? It's 2.28 newtons. All right, so this one here is 2.28 newtons, and this one is also 2.28 newtons. All right, and they want to know what is the combined force of the 2 ropes. The thing that's confusing, let me just read it word for word here. It says, a child's swing is held up by 2 ropes tied to a tree branch that hangs 13 degrees from the vertical. The way it's worded, it makes it sound like the tree branch that they're tied to is at an angle of 13 degrees. But that's not it. The thing that's 13 degrees is the ropes. So if I draw a vertical right here, this angle right here, that's 13 degrees. And same thing with this one. This angle right here is 13 degrees. Okay, so that's supposed to be a degree mark. Okay, so the way that the question is worded is really confusing. But now that we've answered this, hopefully you guys realize that it becomes pretty easy. So what I'm going to do is I'm going to take that 2.28 and I'm going to move it over to this side, because what I want to do is I want to take this vector, oops, I hate it when I do that. I forget that I'm still in eraser mode. Okay, so we're going to take this vector right here, which hopefully you guys recognize is a funky vector. And so what do I mean when I say funky? I mean that it's not a nice, perfectly horizontal or perfectly vertical vector. It goes off at what I like to call a funky angle. And so dealing with funky vectors is really difficult. So what do? Well, what we do is we break it up into its components, or it's something that I like to say, we defunkify the vector. So if I've got that vector going off at a funky angle, that vector is the same thing as if I had a vector that was going perfectly vertical and added to that one that's perfectly horizontal. So these two red vectors, they accomplish the exact same job that my original funky vector accomplished. But the neat thing is that they do it in a non-funky way. They are perfectly vertical and perfectly horizontal. So what we need to do is we need to figure out if this guy here is X and if this guy is Y, what number would X have to be and what number would Y have to be in order for them to do the same job as the original funky vector? Well, if this is the angle that we know the value of, and this guy right here is going to, of course, be the hypotenuse. So X then would be the opposite side. And so which one of our three friends is going to help us out there? Sine, cosine, or tangent? Okay, so this guy here is the opposite side. So cosine is not going to be it, because if we've got opposite and hypotenuse, yeah, okay, sine is what it is. All right, so what we do is we say the sine of an angle is, that's supposed to be a theta there, is defined as. So when I write that equal sign with that extra little line above it, that's a sign that means is defined as. That's something you're going to see an awful lot of this year, so get used to it. Is defined as the opposite divided by the hypotenuse. All right, that's supposed to be a P. That's a terrible P. Okay. All right, that's not much better, is it? Well, that's a P. Don't worry about it. Okay, so now let's put in the numbers here. So we've got the sine of the angle. Well, we know what the angle is. The angle is 13. So that's equal to the opposite side, which we don't know. So we're going to call that X, divided by the hypotenuse, which we do know is 2.28. So I'm thinking we can take this now and we can figure out what X is. If we solve for X, so we multiply both sides by 2.28, then this cancels that and we're left with X equals 2.28 times the sine of 13. So whatever that works out to be, let's see, 2.28 times the sine of 13. So I get 0.513. Okay. All right. So 0.513. And tell you what, now, rather than round it off there, let's carry an extra sig fig along. If you learn nothing nothing else from the midterm, hopefully you remember, don't round off your answers too soon. So let's carry an extra sig fig, or maybe two. So let's call it 0.5128, 0.51289. Okay. All right. So what about y? What would we have to do in order to get y? So, well, relative to that angle that we know, is y the adjacent, opposite, or hypotenuse? Answer, it's adjacent. So which one of our three trig friends is going to help us out? Sine, cosine, or tangent? I need you to type something into the box there. Cosine, okay? Very good. All right, so again, we say the cosine of theta is defined as the adjacent side divided by the hypotenuse. All right, so now let's put in the numbers we know. So the cosine of the angle, well, we know the angle is 13. That's equal to the adjacent, which we don't know, so we called it y, divided by the hypotenuse, which we did know is 2.28. That's supposed to be an 8. All right, so what do? Well, we multiply both sides by 2.28, just like we did before. So we get y equals 2.8 times the cosine of 13. All right, so what does that work out to be? That works out to be 2.2216. So 2.2216. All right, so now watch, this is the beauty of breaking up vectors into their components. So these two red vectors, they do the same job that our original funky vector did. So if we draw the red vectors in there, we don't need the original vector anymore. He's gone, because the two components do the same job, but they do it in a non-funky way. All right. Okay, so now we just do the same thing the other side. But hopefully you can tell from symmetry, I mean, this force is the same, that angle is the same. So what that means is that the numbers are going to be the same. So we can tell then clearly that this guy on the right and this guy on the left, if they're equal and opposite, they're just going to cancel each other out. So we don't even need to worry about them. And so this guy on the right and this guy on the left, they're equal to each other. So all we have to do is take the 2.2216 and double it, and that'll give us the total upward force. Okay. So on this one, I hope you guys agree that the problem wasn't really the physics in this case. The problem was really the question was just not worded very well. Okay, so let's come back to here. I can do one more question if you'd like, but only one more. So if you could only see one more question worked through, which one would you like it to be? Okay, I see number 6. You guys all okay with number 6? Yeah, I think that's a good one. I would agree. That's one that's well worth doing. Okay, so let's open up a whiteboard. Let's do problem number 6 all together here. All right, so what we have is we have a box that is being pulled up into the tree house. So one person in the tree house is standing over kind of to the right, and so they're pulling so that this makes an angle of 55 degrees. And they're pulling with a force of 17.7 newtons. That not very good. Let's try that again. So 17.7 newtons. All right, and then we got the person on the left. They're pulling over like this, and they're pulling with a force of 20.4 newtons. And the angle here is 120 degrees, which we could certainly work with like that. But I found that most students aren't very comfortable with working with that. How about if we figure out what is the angle over on this side? So hopefully you guys know that if this is a straight line, the total there would be 180, right? So this angle that we're interested in here, is going to be 180 minus 120. So this is going to be 60 degrees. So if it helps you to identify it that way, by all means, go ahead and do it. That makes, for most students, that makes it a little easier. And then don't forget that we've also got gravity going down. If you got a different answer than I did, maybe it's because you forgot about gravity. So if I want to know what the force of gravity is, if I want to come up with a number, hopefully you guys remember that it's m times g. And m was, let's see, 3.20. So 3.20 times g, which is 9.8. Okay, so this will tell us what the downward force is. All right, so basically all we need to do is add these vectors. Well, 2 of the vectors are funky. What do? Defunkify them. Now remember, that's a Hendricks term. So if you go to any other school and you talk about defunkifying vectors, the teachers and the other students are going to look at you really weird. Unless you go to the University of Utah. Ames has sent so many students to the University of Utah that if you go up to the campus there and you talk to the physics professor and you talk about defunkifying vectors, he's going to smile and he's going to say, you obviously went to Ames. Okay, so keep that in mind. That's not really an official term. It's just a Hendricks term, but it's one that I like. Okay, so what we need to do then is we need to take this funky vector on the right here and defunkify it. In other words, break it up to its components. So do you agree that if I go straight horizontal and straight up, that these 2 red vectors equal that one blue one? All right, so if this guy is y up here and this guy is x down here, I propose to you that y is going to be equal to 17.7 times the sine of 55 degrees. Now, how did I do that so fast? How was I able to skip a couple steps there? Well, I was able to skip the steps because I've done this so many times, and hopefully by now you have done it so many times too. So, but tell you what, let's go back and let's do all the steps one more time, just for those of you who maybe didn't do the homework as thoroughly as you probably should have. Okay, so y relative to this angle is the opposite side. So if I'm interested in knowing the opposite side and the other side that I know is the hypotenuse, I'm thinking opposite and hypotenuse sounds to me like sine. Okay, so then we say sine theta is defined as opposite over hypotenuse, and so then sine of 55 equals y over 17.7. Okay, so we multiply both sides by 17.7. Okay, and so we get y equals 17.7 sine of 55. So you see, I did it right. It's just I've done it so many times now that I know the pattern. And I would hope that you guys also know the pattern. So let's see if you can figure out what is x. So what is the pattern that I would want to type into my calculator? Don't give me the number. Tell me what is the pattern. If I want to know what x is, it's going to be what times what, or maybe what divided by what. Type it into the chat box. What would I have to type into my calculator? What times what, or what divided by what? Okay, so f cosine theta is what Will is suggesting. You guys agree? Yeah, hypotenuse times, now you said the sine there, Kirkwood. Ouch, okay, it's cosine. Cosine, okay, yeah, okay, that was probably just a typo. Okay, so by now you guys hopefully see the pattern and how it works. So x here is going to equal whatever is the hypotenuse, which in this case is 17.7, times the cosine of 55 degrees. Okay, so now that we've got the components, we don't need the funky vector anymore. Let's just get rid of him. Okay, but over on the left side, we got the same problem there. Over on the left side, we need to defuncify that one. So I propose that that's equal to a blue vector that goes to the left plus a vertical vector that goes up. And hopefully by now you guys have seen the pattern. So this opposite side here is going to be whatever the hypotenuse is, which is 20.4 times the sine of that angle, which is 60. And this side down here is going to equal 20.4 times the cosine of 60. Okay. So by now you should have done enough homework problems that you should recognize the pattern. All right, so we no longer need the funky vector because we've replaced him with his non-funky components. All right, so now just plug and chug. So when you type in when you type it into your calculator, what you're going to find is that the number you get when you do 17.7 cos 55 is going to be basically the same, to within round off error, as 20.4 times cosine 60. So what you're going to find is that these two cancel each other out. So that means the red force to the right and the blue force to the left, they cancel each other out. So then the only things we're left with are the the vertical forces. So if we just take this guy, add it to this guy, and then don't forget to subtract mg. A lot of people, they forget about the mg, but yeah, don't leave that out. So just add those up, and if you do it right, you should get the answer shown here. And notice that the answer here, it only has an upward component. There is no right or left component because like we've discovered, the force to the right and the force to the left cancel each other out. All right, so that's all that we can really spend time on from last night's homework. So if you have a question that we didn't have time to answer, send me an email. Or you could wait until Friday and we could go over it on Friday. Whichever one works the best for you. I'll be glad to help you. So let's move on to the new material for tonight. So go back to here. Okay, so tonight So we're not going to finish up chapter 5 tonight. Theoretically, we could have, but I think it just would have been too much to handle on one night. So we're just going to do part of chapter 5, and then we'll come back next time we meet and we'll finish up chapter 5, and that'll give us a little bit of time to review and then take the test. Okay, so why is it doing this? All right, so today we are going to deal with friction. I see somebody just typed something into the chat box, but for some reason, oh, okay. Your brain composition, thanks me. All right, well, good. All right, so up until now, we have always ignored friction. But friction is a really important concept that you absolutely need to understand. So let's take a look at this picture over here on the upper left here. So we've got some construction worker pushing on a box, and there is friction. So the construction worker is pushing to the right, but friction is opposing him. It's the resistance force. And so what we need to do is we need to understand why is there friction and how could we calculate what the friction force is. So if we were to just do a bunch of experiments, remember the very first day of class where we did all those experiments where we said that, we've got an independent variable and a dependent variable, and we need to make predictions about whether it's direct or inverse and linear or nonlinear. Okay, so what we're going to do is we're going to change the weight that's in the box. So the first time that we do the experiment, we're just going to have him pushing an empty box that doesn't weigh very much. And so hopefully you guys realize that if you're pushing an empty box, then the resistance force is not very much. Pretty easy to push an empty box. So now let's put a couple of rocks in the box. And so he starts pushing it. And so it's going to be harder. And then, so the more rocks we put in the box, in other words, the heavier the box is, the harder it's going to be to push it across this rough floor that's giving us some friction resistance. So the best way to understand this, I think, is to do a free body diagram of all the forces that are acting on the box. Now, when I do free body diagrams, I like to do them a certain way, and I highly recommend that you guys do them the same way. Instead of drawing the friction force acting down here, I like to draw the friction force. In fact, all of the forces, I like it so the tail of the arrow starts in the middle of the object, and then the force goes off whatever direction the force is pushing. Now, it doesn't, it's not essential to do it this way, but I find that it's helpful because sometimes it's confusing as to what force is acting on what object. So if we do it my way, it's always clear that this force right here, which we're going to call the force of friction, big F means force, little f means friction, is clear that the force of friction is a force that's acting on the box. So even though it's actually, really technically, this is the location down here. That is, in fact, where it's acting. But I like to draw it this way. Okay, so what we're going to do then is we're going to take that vector and we're going to move it up. So here. And then the guy pushing, I'm going to do the same thing with that. I like to draw it so that the center of the arrow is in the center, or so the tail of the arrow is acting on the, is drawn in the center of the box. So this is the force of the guy pushing. All right. Now, these are not the only forces acting on the box. Hopefully you guys realize that we've also got gravity pulling on the box, right? So we're going to have gravity going down. So that's mg. But the force, the box is not moving downward. So if there's a force pulling it downward and yet it's not moving downward, there must be some upward force. And that would be the force. So as Sam says here, it's the force of the ground, okay, which is exactly right. Okay, so the force of the ground pushing on the box. Well, this is a very important concept. And so what we're going to do, this is so important that we're going to give it a special name. Instead of calling it the force of the ground pushing on it, we are going to call it the normal force. Now, students always get a little bit perplexed here when I call it the normal force. because normal to most people means not strange. So the normal force, does that mean the force that isn't strange? Does that mean it's not a funky force? Is that what you mean? No, that's not what I mean. When a math teacher talks about something being normal to something else, what the math teacher is saying is perpendicular. So if I've got some plane here, I've got a piece of paper, this is a plane, and I've got some line here, and this line is perpendicular to the paper, then a mathematician would say that this line is normal to the paper. Now, up until now, your math teachers may not have used that term, but when you take advanced math, you're going to hear that a lot. So normal means perpendicular. So if we do our free body diagram here, which got erased when I stopped sharing. So we got mg going down, and then the upward force, we're going to call that Fn, which is the normal force. And then we've got the guy pushing, so that's Fp, and we got the friction, Ff. Okay, so the more weight we put in the box, the more the normal force is going to be. In other words, the more the squeezing force is between the box and the floor. So if it helps you to think of it that way, think of it as the squeezing force. Because the more force we are using when we squeeze the box and the floor together, that is what determines how much friction we're going to have. So the more squeezing force we have, the more friction we're going to have. All right, so now, if we do this experiment where the independent variable is the normal force, or in other words, the squeezing force, okay? And our dependent variable is the resistance force that we feel when we push this box across the floor. What we're going to find is we get a linear graph. Now, it's not obvious why it has to be linear. I mean, you would think in theory it could be nonlinear, but when we do the experiment, it turns out that it's always a linear relationship. But the slope of the line depends on what the surface looks like. If this floor was really rough, like sandpaper, then we would get this graph that you see right there. And so what that means is if we were to exert a little bit of, or if we were to put a little, just a few rocks into the box so that the normal force is relatively low, then we get a friction force that's equal to that. If we double the amount of weight that's in the box, well, it turns out that the friction force will be exactly double. And if we triple the amount of weight that's in the box, then the friction force is going to be triple. So it's a linear relationship here. But what if we switch to a different type of surface? Okay, what if instead of having a really rough sandpaper-like surface, what if we have a very highly polished, smoothed floor or a smooth table? So this same amount of weight that we have in the box, it's only going to give us this much friction force right here. And when we double it, okay, it will still double it, but it'll be double a much smaller number. And when we triple it, okay, it'll still be triple, but it'll be triple a smaller number. So these relationships here, they are going to be linear, but the slope of the line is going to be different depending on how rough the surfaces are. Does that make sense? So if I want to come up with an equation here, so this is my independent variable, this is my dependent variable. So y equals mx plus b, but the y is my dependent variable. So that's going to be the force of friction. Now the b is my y-intercept, and you can see here the y-intercept is 0 for all cases. So that means we have no b value, okay? The x value, well, that's our normal force. So I'm going to call that Fn. And then the slope here, well, that depends on how rough the surface was. So I could put an m value in here, but physicists figure this is important, and it's such an important concept that we're going to give it its own special letter. So we are going to call it mu. So this is a Greek letter that some of you may have seen before. It's pronounced mu, and basically it's a U with a little tail on the right, where the tail on the right is a little bit longer than the tail on the left. And if you want to see what it looks like in printed form, just look up here to the right. So these letters that I just circled on the right there, those are the mu letters. And these numbers that you see here, these are what the slope would be. So if we perform this experiment where we use rubber on dry concrete, then these are the slopes that we would get. Now, but why do we have two of them? Why wouldn't it just be one slope? Why do we have two different values here? Well, the answer for that is the reason we have two different values there is because it depends on whether the box is moving or whether the box is stationary. So let's say that I've got, this is my tabletop. It's actually a book, but I'm going to use it as a tabletop. And here is a stapler. And so it's sitting there at rest. So when I push on this stapler, if I just give it a little tiny push, it doesn't move. Push it a little harder, still doesn't move, right? So what I'm going to do is I'm going to push until this thing finally moves. And I'm going to see how much force does it take to finally move. So let's just make up some numbers here. Let's pretend that in order to get this stapler to move, I have to push with 15 newtons of force. Let's just experimentally, let's pretend I did the experiment. That's what I found. Okay. So then the force of friction that I need to overcome is 15 newtons. But what if the stapler was already moving? Okay. And so what I want to do is I want to see how much force does it take to keep the stapler moving, not to start it moving, but to keep it moving once it is moving. Now, most people would say, well, if it took 15 newtons to get the stapler moving, then in order to keep it moving, wouldn't it be the same 15 newtons? No, it's not. That's not the way it works. So it takes 15 newtons to get it moving. But once it's moving, if I want to keep it moving at a constant speed, what I'll find is that it takes less force, maybe let's say 12 newtons. Okay. So the amount of friction that you have when an object is at rest is different than the amount of friction that you have when something is moving. So that's the reason why we have two mu values. We have one mu value, which is mu s, where s means static, or it means, it's another way of saying it's not moving. And then we got another mu value, which is called mu k, where k stands for kinetic, which means that it is moving. All right. So if I'm interested in the static case, then the slopes of these lines would have to be slopes that I got when I did an experiment where I was just trying to figure out how much force does it take to start the thing moving. But if, on the other hand, I'm interested in the kinetic case, then these would be the slopes of the lines that I get when I experiment with how much force do I need to keep the thing moving at a constant pace. Okay. Now, I think it's really important that we take a minute to understand why the static friction is greater than the kinetic friction. I'm willing to bet that some of you probably know. Anybody want to unmute yourself or type something in the chat box? Anybody have any theories as to why it is that static friction turns out to be stronger than kinetic friction? Nobody? Okay, all right. Well, okay, then I'll help you out. Okay, so look at it at the microscopic level. So first ask, why is there even friction at all? Well, when we were talking about it before, we were talking about the surface roughness as being the factor, right? So if we push a box across the floor where that floor is made of sandpaper, clearly there's going to be more friction than if it was a polished floor. So it's the roughness here. So if I look at the floor here, so here is the floor, And if you look at it, even if it's even if it's a highly polished floor, if you look at it at the microscopic level, what you're going to find is there is roughness, okay, at the microscopic level. And so then here's the box that's sitting on top of it. And the box might look smooth, but if we look at it at the microscopic level, we'll find out that the box is rough too. So if what we want to do is we want to pull this box across the floor, well, the reason that we get resistance is because of all the roughness here. All of the little bumps on the floor and the bumps on the box, they all hit into each other. And so we have to overcome all of the bumps hitting on the bumps. Okay, so that is the reason why we have friction. But that doesn't answer the question of why is the static friction greater than the kinetic friction. Okay, so Adam is suggesting that maybe it has something to do with the repulsion that the electrons give. Okay, I think you're onto something there, Adam. It sounds like maybe you have taken a chemistry class, which, by the way, almost all of you have taken chemistry, and the few of you that haven't taken it, you're taking it now. So think back into your chemistry class. Do you remember something called Van der Waals Forces? Remember that? Yeah. Okay. So if you have a molecule from the box that's up on top here, and it's in physical contact with a molecule from the bottom, okay, they just happen to be in those little bumps that are physically touching each other. So what's happening is that these two molecules, because they're touching each other, they can exchange electrons and they can form a weak bond, which is called a van der Waals bond. And so that means that but they're only going to do that if they are not moving relative to each other. Okay. If the box is sliding, then there's no chance for these van der Waals bonds to form. But if the box is just sitting there at rest, then it can form these van der Waals bonds. And so then when I want to make the box move, not only do I have to overcome the surface roughness, but I also have to break these van der Waals bonds. And so that's the reason why static friction is greater than kinetic friction. Right? Now, there is one other thing that we need to talk about before, and then we'll do a couple example problems. Okay, but there's one thing that we need to talk about. If we write the equation as F friction equals mu times the normal force, that doesn't really capture what's happening in the case of a static situation. If there's a static situation, then we got a problem with this equation. And so let me talk through an example here and let's see if you can figure out what's the problem. Right? Let's suppose that, actually, let's go back to this example here. Remember I said that it took 15 newtons of force in order to break the thing to move it free. So let's suppose that I'm pushing with 1 Newton of force. How much is the friction force that's opposing me? Is it going to be 15 newtons or is it going to be 1 Newton? You guys type into the chat box. If I'm pushing with 1 Newton of force and the stapler is not moving, yeah, that means that the friction force, the resistance force is 1 Newton. What if I push with 2 newtons of force? Then the stapler doesn't move. So what is the friction force going to be then? It's going to be 2. So do you see the problem with the equation here? If I say that the friction force is equal to mu times n, that doesn't really capture what's happening in the static case, because in the static case, the friction force can adjust itself to match whatever I'm doing. But it can only do that up to a certain point. Once I get to 15 newtons on my stapler here, that's the maximum it can possibly do. So if I push with 15.0001 newtons, then all of a sudden it breaks free. All right, so what we need to do here is, instead of saying that the friction force is equal to mu times Fn, what we should do we should say that the friction force is less than or equal to mu s times Fn. Okay, so in the case of a static situation, this is not an equal sign. It's a less than or equal sign. But what if it's not static? What if it's a kinetic case? Okay, so if it's a kinetic case, so hopefully you guys remember that the force of friction is less if it's kinetic. So if I were to push on that stapler with 15 newtons, I would find out that that stapler is going to accelerate because the force of friction we decided was, you know, when I just was making up numbers, I said that it was 12. Okay, so once it starts moving, it takes less force to keep it moving than it did to start it moving. But here's the interesting thing. Okay, so again, okay, if I were to do an experiment, if I push on this stapler, so once I get it moving, okay, so I got to push 15 to get it moving, but once I get it moving, okay, if I push it slowly, I find out that the resistance force is going to be 12 newtons. If I push it a little bit faster, the resistance force is still 12 newtons. Okay, and let's suppose that I push it with 20 newtons. So in that case, it's going to accelerate. And if I were to calculate the acceleration and figure out what the net force is, I would find out that the resistance force is still 12 newtons. So when something is moving, the resistance force can only be one value. It doesn't matter whether I'm pushing with 12 newtons or whether I'm pushing with 20 newtons or whether I'm only pushing with 3 newtons. Okay, the friction force will always be the same value, but only if it's moving. Okay, the static case is different. All right, so hopefully now you can understand why it is that in the book here, they give you, oops, sorry. Okay, you'll see when you read the book prior to doing the homework, because I know you always read the book before you do the homework, right? So that's the reason why you're going to see that if it's a kinetic case, then it's an equal sign. But if it's a static case, then it is not an equal sign, it's a less than or equal sign. Okay, so that's all the new material that I wanted to talk about. Before I turn you loose, it's probably a good idea if we do a couple sample problems like you might see in the homework. All right, so let me share my whiteboard and let's make up some problems kind of like you might see in the homework. So let's say that we've got the floor, we've got a box on the floor, and this is a wood box sitting on a wood floor. And the mass of the box is 7.8 kilograms. And so the question says, if I push on this box with a force of 21 newtons, will the box move? Okay, so I want you guys to take a minute and see if you can figure that out. Will the box move? Now, you're going to need to know what is the coefficient of friction for wood on wood, which you probably don't have memorized. It was on the table that I showed you the earlier, which by the way, I copied out of the books. So let's look. So if we look on that table, we're going to find that mu s for wood on wood is 0.5, and mu k for wood on wood, I think it was 0.2. I'm pretty sure that's what it was. Let me just make sure. I'd hate to quote something wrong there. Yes, it was 0.2. Okay, so what do you think? Will the box move? I need to see answers in the chat box. And when you type in the answer to the chat box, type it in a private message, not a public message, so that other people don't see. Is the box going to move or not? So I'm seeing a yes with a question mark. Now I'm seeing a yes without a question mark. Okay, so I'm seeing a whole bunch of yeses. All right, okay, so let's make sure that I agree. So I'm going to work through this problem. Okay, so first step is I'm going to do a free body diagram. So I've got mg going down. I've got the normal force going up. I've got me pushing, which I prefer to draw over here. This is the force of me pushing. Okay, and then the friction force is going to be over here. All right. Okay, now we know that the normal force and mg, those are equal to each other. So let's go back to the definition of friction. So the force of friction in the static case is less than or equal to mu s times the normal force. But the normal force is mg. So it means the force of friction is less than or equal to mu s times mg. All right, so mu s is 0.5, m is 7.8, g is 9.8. So when I punch that into my calculator, so 0.5 times 7.8 times 9.8, okay. So I get that the force of friction less than or equal to 38.22. So what this means is that friction can exert a maximum of 38.22 newtons. So if I am pushing with 21 newtons, I'm pushing with less than what friction is capable of pushing back with. So those of you who said, yes, the box will move, I got bad news for you. No, it's not. So if I push with anything up to, but not exceeding 38.22 newtons, the force of friction will be able to match what I'm doing. If I want that box to move, I have to push with 38.23 or more. Otherwise, that box is not going to move. Okay. All right. Let's do one more problem, like you might see in the homework tonight. Let's take that exact same box where what was the mass? So mass was 7.8, right? 7.8. So we know that the maximum force that the friction can exert is 38.22 newtons. So let's push with a force that's greater than that, right? So let's push with a force of 51 newtons. So we know that the box is going to move, right? Because we figured out the maximum friction force for the static case was 38. So I want to know, what is the acceleration of the box going to be? Well, let's finish our free body diagram. We've got mg going down. We've got the normal force going up. And we've got the friction force that opposes us. Now, you might be tempted to say that the friction force is 38.22, but that would be wrong, because that was the case for static friction. And that's the force that it would take to not only overcome the roughness of the surface, but also to break the bonds. Now, once it's moving, we don't need to worry about breaking the bonds. Okay, so the friction force is going to drop. It's not going to be 38 once it starts moving. So if we want to know what the friction force is when it's moving, we go back. So the force of friction, now this time it's an equal sign because it's moving. And so this is going to be mu k times mg. So mu k for wood on wood is 0.2. M is still 7.8 and G is still 9.8. So the force of friction in this case is 0.2 times all of those guys. So I'm getting that the force of friction works out to be 15.29. Okay. So on my free body diagram here, let me get rid of this. So my friction force is going to be 15.22. All right. So now, for as far as acceleration goes, we don't need to worry about mg and fn because they're going to cancel each other out. So if we want to know what the acceleration is, well, let's make a little room here so we can do some writing. Okay. If only there was an equation that related force, mass, and acceleration. Can anybody think of any equations that relate force, mass, and acceleration? Come on, type it into the chat box. Yes, F equals ma. Very good. All right, so F equals ma, but remember, that was the junior high school version. The high school version, we have to put a sigma in front of there because there might be more than one force acting on the box. And in fact, this time there is, all right? So when we do sigma F, we're gonna have to do 51, because that goes in the plus direction, and then minus 15.22, that's equal to ma. So A then equals whatever this is divided by M. So what is 51 minus 15.22 divided by 7.8? So 51 minus 15.22 equals, oops. Now make sure that you use your parentheses right. If you don't use parentheses on the top there, you're going to get the wrong answer. And let's see. So in fact, I just typed it in wrong. Let me do that again. 15 minus 15.22 close parenthesis divided by 7.8. Okay, so I get that the acceleration is going to be 4.507, which is too many sig figs, so I'll round that off. So the acceleration then is going to be 4.5 meters per second. That's going to be our answer. All right. So these are the types of problems that you're going to see in tonight's homework. Hopefully you'll agree that they're not too hard if you understand the basics of what is friction and why does friction occur, and why is static friction given with a less than or equal to sign, whereas kinetic friction is given with an equal sign. Hopefully it'll all work out. Okay, so let's end the class right now. We still have about 10 minutes left. There's probably not going to be enough time for you to finish the quiz, but I didn't put a time limit on the quiz. So if you want to start it now and finish later, that's okay. Or if you just want to wait and take the quiz this evening, that's okay too. But do not forget to take the quiz. Now, you're probably going to want to know what the homework is, huh? All right, so here's the homework, or you could, of course, just look in Canvas. So section 5.2, problems 17 through 21, that is your homework for tonight. Do not forget, take the quiz. It is now unlocked. And so if you wanted to take it now, you could. So are there any questions before I end the class? Well, how about this? Let me turn off the recording because some of you might be shy about asking questions if you know it's being recorded. So I'm going to turn off the recording now.